Hey everyone, it's Dr. Garner here. I'm going to pick up with where we left off in the last video by looking at isotopes. So in the last video we saw that isotopes were versions of an element that possessed different numbers of neutrons. We also saw in the last video that neutrons contain a significant amount of mass. So because of that, different isotopes are going to have different masses owing to the different numbers of neutrons that they contain. So isotopes with more neutrons are going to have a higher mass. And we can describe the mass associated with an isotope in terms of what we call the atomic mass or the isotopic mass. You'll hear both of these terms used to describe this concept. So the atomic mass or the isotopic mass, it's the mass of a single atom of a particular isotope. And then we have a couple of examples here. So we have listed here carbon-12, carbon-13, and carbon-14. So as we saw in the last video, carbon-12 contains 6 neutrons and 6 protons. We also saw that it was the basis of defining the unit of the AMU, or the atomic mass unit. So an AMU was defined as being exactly 1/12 of a carbon-12 atom. Therefore, a carbon-12 atom is going to have a mass of exactly 12 AMU. So if we go from carbon-12 to carbon-13, of course the difference there is that we've just added 1 extra neutron. So we now have 6 protons and 7 neutrons. So our atomic mass increases by about 1 atomic mass unit, since a neutron has a mass of about 1 AMU. So our mass goes up to 13. Again, it's not exactly 13, but it's approximately equal to 13. If we continue on to carbon-14, again we add 1 more neutron, so now we have 8 neutrons and 6 protons. So our mass number is 14, and our isotopic mass roughly equals that mass number. So again, it's approximately 14. So you can see this trend here, that the mass number of an isotope is going to be approximately equal to the isotopic mass of that particular isotope. All right, so don't conflate this term atomic mass with the concept of atomic weight. So atomic weight, this is the value that's found on the periodic table. The atomic weight represents an average of all of the masses of all of the isotopes of a particular element, weighted according to how abundant or how common that particular isotope is. You'll also hear this quantity atomic weight, you'll also hear this described as relative atomic mass or average atomic mass. So if you look at the periodic table for carbon, its atomic weight is the value that's given there of 12.0107 AMU. This atomic weight is the sum of the masses of each of these isotopes of carbon multiplied by how abundant that particular isotope of carbon is. So we can kind of show an example here for carbon. Its atomic weight is 12.0107 AMU. So you could get to that same value by adding up the atomic masses of each isotope times the abundance of those isotopes. So let's do that here. So let's start with carbon-12. We're going to have a term like this for every one of these 3 isotopes. So let's start with carbon-12. Its atomic mass is 12 AMU. So I'll start with that. Then I'm going to multiply that by the abundance of carbon-12. So in other words, how common carbon-12 is. And it turns out that carbon-12 represents almost all of the carbon on Earth. So about 99% of the Earth's carbon has 6 neutrons and is therefore carbon-12. So carbon-12 is extremely common. It represents most of the carbon on Earth, about 99%. All right, so that's my first term for carbon-12. But since I'm summing here, that's what the sigma represents, a sum, I'm going to add to that another term representing carbon-13. So I'm going to add, and then I'm going to do the same thing for carbon-13. I'm going to take its atomic mass of about 13 AMU and multiply by its relative abundance. And it turns out that carbon-13 represents pretty much all of the other carbon on Earth. So about 99% of carbon is carbon-12. The other 1% is carbon-13. So we're just showing that percentage here as a decimal. So the abundance of carbon-13 is 1%, or 0.0107, written as a decimal. So as you can imagine, we've accounted for pretty much all of the carbon now. So that must mean that the last term for carbon-14 is pretty much going to be negligible, because the abundance of carbon-14 is incredibly small relative to the abundance of carbon-13 and carbon-12. So carbon-14 only existed in trace quantities on Earth, so we don't really have to worry about that last term there. And the math here should check out. If you work out the math here, you should end up with the same value that's found on the periodic table. So that's where that quantity on the periodic table is coming from. All right, let's try out a couple of example problems here. This one's really more of a follow-up to what we saw in the last video, but it doesn't hurt to review, so we'll try this one out now. Again, I would always suggest pausing the video and trying this question out on your own first, Then once you figured it out, take a look at the solution. All right, so in this question, we're being asked which of the following is not an isotope of silicon-30. So we're being shown here this nuclear symbol for silicon-30. Again, this bottom left number is our atomic number of 14. So that tells you how many protons there are. The top left number, that's the mass number of 30. That's the sum of protons and neutrons. So if there are 14 protons, there must be 16 neutrons to give us this sum here of 30. All right, so it wants to know which of these is not an isotope of silicon-30. So let's look at these one at a time. In choice A, we have an atom with 14 protons and 15 neutrons. So this is an isotope of silicon-30. This is going to be silicon-29. It's still silicon because there are still 14 protons. So having 14 protons defines this as being silicon. That's our atomic number of 14, which corresponds on the periodic table to silicon. In terms of our mass number here, we can take our 14 protons plus our 15 neutrons to give us our mass number of 29. So this meets the definition of an isotope. It's the same element, but it differs in the number of neutrons that it has. It's still silicon, but it has a different number of neutrons. It's a different isotope of silicon. All right, we can look here at choice B as well. So this one's a little bit simpler. So we know that it's silicon because they tell us that very explicitly, so it's still silicon. And we know that the mass number is different as well, so there must be a different number of neutrons. So this is also going to be an isotope of silicon-30. It's the same element, but it has a different mass number, so it must have a different number of neutrons. All right, so choice C must be our answer here, and choice C is not an isotope of silicon-30 because it's not silicon, it's a different element. So in choice C, we're told that this atom has 16 protons and 14 neutrons. Remember, it's the number of protons that defines which element this is. So this element would have an atomic number of 16, and if you look that up on the periodic table, you'll see that an atomic number of 16 corresponds to sulfur, so it's a different element. So even though it has the same mass number, but the fact that it's a different element disqualifies it from being an isotope, so it's not an isotope of silicon-30. All right, so our answer there was C. All right, we have another question here as well. This one asks, silicon has 3 naturally occurring isotopes, and we're asked which of these 3 isotopes is the most abundant. Again, I would encourage you to take a moment to work this out on your own. Then once you're ready to watch the video, just unpause. All right, so we're told here that silicon has these 3 isotopes, silicon-28, silicon-29, and silicon-30, and they give us the isotopic masses for each of these isotopes. Again, as a general trend, the mass number is always going to be roughly equal to this isotopic mass. All right, so we can figure out which isotope here is most common or most abundant by looking at the atomic weight of silicon on the periodic table. If you look at this number for silicon on the periodic table, you see that it has an atomic weight of 28.086 AMU. So this represents the weighted average of these 3 masses weighted according to how abundant each isotope is. And what you'll see here is that this value of 28.086 is almost identical to the mass of silicon-28. So what that means is that the abundance of silicon-28 must be really high, so that that weighted average is close in value to this value of 27.98. So therefore, most silicon must be silicon-28, since that weighted average is close to the mass of silicon-28. So A is going to be our answer here. And again, if you actually look up these values, what you'll see is that this is true. So silicon-28 has an abundance of about 92.2%. Silicon-29 would have an abundance of about 4.7%, and silicon-30 would have an abundance of about 3.1%. Again, you wouldn't necessarily know these values without looking them up, but from the mass on the periodic table, you should generally be able to conclude that silicon-28 was the most abundant, since that weighted average was close in value to the mass of silicon-28. All right, we'll stop there for this video. Thank you for watching.